Today's lecture is on the model building approach as an alternative for the historical simulation approach. So let me begin again, say with an outline of what I will discuss today. There's two topics on the agenda for today. There's the linear portfolio model and there is handling bond portfolios. There's a lot of other material that will be covered in the book, but there will be no emphasis on the remainder, and I will also explain why. So let me start with providing you some background. In particular, if we take a portfolio perspective then and we look to the uncertain future, then what we are interested at is to understand how each asset in your portfolio could move into the future, what kind of different scenarios would be possible, but also to what extent the assets co-move with each other. And we have seen before, when we look to the historical simulation approach, that we could look to historical realizations to have an assessment of these elements. So what we will be doing today is we will look to particular cases where instead of relying on simulation, we have an analytical format for the uncertain future portfolio elements. So an analytical model means that we have a more concise representation, which then also makes it analytically tractable to afterwards not only decide, for example, on optimal portfolio weights, but also do value at risk calculations in an analytical manner. So this analytical model or linear model that we will be discussing today is also referred to as the variance-covariance approach, as you will see in a minute why. And the main advantage of this approach is that we don't have to rely on simulation, and for that reason it's much faster, and then also see analytically you could see what the properties are of all the elements in the portfolio and the portfolio risk and so on. So as I said, we will limit ourselves to one particular case when we look to this model representation, the model building approach. We will only look to those cases where we could say, well, on the left-hand side, there is, for example, a portfolio value or a change in the portfolio value or portfolio return or change in the portfolio return, which is then linearly related to market variables, uncertain variables, which are on the right-hand side. And in particular, we limit ourselves to the case where it's a linear relationship. So, and if it's not linear, then we will see whether we could make it linear, and otherwise we will rely on alternative measures. So this model building approach is in particular in use when institutions have to choose optimal portfolio compositions. Think, for example, about, well, how much to invest in stocks, in bonds, in real estate, and so on. And very often the time horizon is longer than a day. Very often you have to think of time horizons of a year or longer. So what to do if we are not in the case of this linear relationship between a portfolio return and market variables or asset returns, for example? Well, there is three possible alternatives that I've listed here. Well, first thing that you could do is you could say, well, I'm going to disentangle this nonlinear relationship into a linear effect and the remainder part, and I just ignore the remainder part. So I'm only looking then to linear effects between the left-hand side variable and the right-hand side variables. That's one thing that very often works. So we saw that working, say, in the bond return case. Second alternative, what you will see quite frequently, is that we simply rely on Monte Carlo simulation. So we draw random scenarios from the underlying market variables, and then with each draw, there will be a realization for example, the portfolio return, and doing that many times provides us a whole distribution function of the portfolio return, which then also allows us to make expected return and risk assessments. So think about value at risk calculations or expected shortfall calculations. And then the third alternative is simply to rely on historical simulation, look to past realizations of market variables, to the way that they have moved, to the way that they have co-moved, and use that as potential scenarios for the future. So that's three alternatives. Now, so we will assume that we are in the particular case of a linear relationship between a portfolio value or change in the portfolio value and underlying market variables. Then, so there's other chapters in the book, other sections in the book that also propose model approaches. These are in particular cases where the relationship in fact is nonlinear and where it would be possible with all sorts of adjustments to arrive at the model approaches. So I will not put any emphasis on that because in my opinion it's much easier and more common to use simulation methods in those cases. So one of the three cases that we just discussed. So focus on the linear portfolio model approach, and on term structure principal components approach will be what's on the agenda for the remainder of this lecture. So let's start with the linear portfolio model. We take a portfolio perspective, so that means that we have a portfolio which has a value denoted with capital P. This value is an amount, let's say it's a dollar amount, and then this portfolio is built up out of n assets, small n assets. And each asset has a particular value, and with delta I, we denote the amount, the dollar amount that has been invested, or that it's the current value of asset I. So then if you look to the first equation on this slide, it says, well, my portfolio value P is simply the sum of the values of all the individual assets. So it's a sum over I is 1 to n of delta I. Then suppose that I would denote with Ri a daily return of asset I, then it's very easy to calculate a portfolio change value or portfolio income value, because simply what you do then is that you multiply each asset value with the return that applies. So those delta I times Ri is then the return on asset I. If I add it up over all the assets I, then I get the change in the value of the portfolio P. So delta P denotes the change in the value. So the original value is P. Now there will be an increase or decrease of delta P, well, depending upon, say, how the returns affect the values of the individual assets. Then once I have that value, the change in portfolio value, which is a dollar amount, then I can of course normalize that by dividing the delta P by P, which then gives me the return on the portfolio value, which I will denote with RP, portfolio return, which then simply is the weighted sum of the returns on the assets. So with WI, I denote the weight of asset I in portfolio P. Ri was the return at a particular day on asset I. So if I multiply the two with each other and I add them up over all assets in the portfolio, I get the portfolio return. So the portfolio return, very simply, is the weighted return of the individual assets. And the weights obviously add up to 1. So how to define the weight? Well, the weight of asset I is simply the value of asset I, delta I, divided by the total portfolio value P. So very standard representation of a model, of a portfolio model. Now, we are going to consider the returns on each asset as the underlying market variables. So these are uncertain. So we have n assets, so then we also have n potential returns that could occur from today into the future. And we make the assumption that these returns are normally distributed. They are multivariate normally distributed. They have a mean vector including the mean returns, mu1 to mu_n, where mu_i is the expected return on asset I. And there is the variance covariance matrix. That's also why we refer to the linear portfolio model as the variance covariance matrix model, which then includes the movement of the individual assets, which are on the diagonal, represented by the variances, sigma 1 squared, sigma 2 squared, until sigma n squared. And there are also the co-movements included in this representation, which are the covariance elements which are on the off-diagonal entries of the matrix, of the covariance matrix. And there, for example, rho ni sigma n sigma 1 denotes the covariance between return 1 and return n. So where sigma n is the standard deviation of return n, sigma 1 is the standard deviation of return 1, and rho n1 is the correlation, which is a standardized measure, between the return of asset n and asset 1. Obviously, the correlation between an asset and itself, so for example, rho 1 is equal to 1, and so rho n is also equal to 1. These elements in this multivariate normal distribution function, so the mu's and the sigmas and the correlations, are the key ingredients to represent the uncertain future. And so once more, the mu and the sigma are the mean and the standard deviations of return I, and then rho ij is the correlation between return I and return j. And we have to see how we could determine estimates for these relevant parameters. And there, well, in the following, we will look to two particular cases. We will look to the unconditional representation, where we really say, well, we simply look to historical observations, and we take then the mean of all the historical observations to represent the expected returns. We take the standard deviation of all the historical returns to have the estimate for the sigmas, and we take the correlation between all the historical returns to get the correlations. And then an alternative is to say, well, we will look to exponentially weighted moving averages, where we are going to update the parameters, in particular the variance and covariances, in such a way that they represent the regime that they are in. So the portfolio return, once more stated, is the weighted average, is the weighted average of all the individual returns of all the assets in the portfolio and assets in the portfolio. And we just said, well, then this Ri, all these R's, they are together multivariate normally distributed. So if you take a weighted sum of that, then it means that you get a return for the portfolio, which then is univariate normally distributed, so which has an expected return of mu p, which is a scalar element, and has a variance of sigma p square, which also is a scalar element. So how to define these expected returns and the variance of the portfolio? Well, for the mean of the portfolio, for the expected return of the portfolio, you take the weighted average of the means of all the individual assets. That's the formula in the center of this slide. And for the variance of the portfolio, you're going to take the weighted sum of all the covariance elements. So I'm going to look to each entry in the covariance matrix, and I'm going to multiply that with the weight of one asset and the weight of the other asset. And then I'm going to add up all these elements together, which provides me then the variance of the portfolio. So rather an easy way to do that. Now, suppose that I've done that. Suppose that I've calculated the mean of the portfolio, the expected return, and the variance of the portfolio. Then it's going to be rather easy to do risk assessments. So when this is a daily portfolio return, then we know that the mean very often is small and could even be ignored. You could set it to 0. I've here at least listed the formulas including the means, so even though the effect is small, then it's clear. So let's recall how we defined the value at risk of a portfolio. So now we are looking to the value at risk of the portfolio return in this case. The critical level that we apply in this case, as that's the probability mass in the left tail. So I said, for example, that's 1%. So there's a low probability that we have returns even worse than what we will find with the value at risk. So the X is set to a low probability number, and the capital T defines the horizon at which we look. So if we look at 1 day in this case, so if these returns are defined with daily frequency, and we look to a 1-day value at risk, then the T is 1. If we look to a 10-day value at risk, then we need to set T equal to 10. So it says the value at risk is then the mean effect, take the mean of the portfolio times the time horizon, plus the critical value of the standard normal distributed function, evaluated at this low probability level in the left tail, so at the 1%, so X is 1%, for example, times the standard deviation of the portfolio return, and times the square root of the time horizon that we look at. So once more, if we look to a time horizon of 1, then we take the square root of 1. If we look to a time horizon of 10 days, then we take the square root of 10 in this case. So this formula is rather easy to apply. So the standard normal distribution function, so that critical value that you require there, you look it up in the table for the standard normal distribution function. The mean and the standard deviation, you have estimated them before, using as input the historical variances and covariances and returns, mean returns of the underlying assets in the portfolio. And T is simply the time horizon that you set. Then the second risk measure that we often use is expected shortfall. Same thing applies there. We look to a T-day assessment, so an out of sample period of T days. And also here the critical value in the left tail of the return distribution is also set to X, which then also is, for example, 1%. Then for the expected shortfall, you use the exact same elements as you use for the value at risk. So you need the mean portfolio return, you need the time horizon, you need the standard deviation of the portfolio return, you need the critical value, so the 1%, so that's the X, and you need to have that evaluated in the standard normal distribution function. So let's apply this simple linear model to a real life case. So we look to a portfolio which is at 29th of March 2019, so last month, is worth 1 million. And this portfolio is invested in 4 stock indices: the Dow Jones Industrial Average, the CAC 40, the FTSE 100, and the Nikkei 225. And between parentheses is the portfolio weight of these 4 investments. So 40% in the Dow Jones Industrial Average, 20% in the CAC 40, 30% in the FTSE 100, and 10% in the Nikkei 225. Because these returns, these indices are listed in different jurisdictions, in different countries, different currencies applies, and in order to put them in a portfolio context, we first have to make sure that we denote them all in the same currency. So what we will be doing here, we assume that the investor is interested in a dollar return, which means that we assume that all the currency risk has been hedged, so all the dollar risk, all the risk has been hedged, so that we can express everything in dollar values. So we can forget now about currency risk. So the only focus is return risk. So we assume, so we can work further on under the assumption that all these returns are dollar denominated, and we simply can add them up. We will be looking to a monthly frequency, so not to a daily frequency. a monthly frequency of historical observations on these 4 indices. So that's a period from the 30th of September 1997 to the 29th of March 2019. So that means that I have 259 price observations. If I'm going to calculate returns for each index, then it means that I have 258 return observations. So I've done that, I've calculated the returns, and I've also provided a plot here of the 4 indices. And what I did is that the first value of the index, of all the 4 indices, was reset to 100. So to give you, and I did that at September 1997. So I did that to give you an idea of how the 4 indices moved compared to each other. So 1997 September, it's just outside this graph. This graph starts at 1998, so that's why you don't see them all starting at 100, but that's just before. And then we see that initially the CAC 40, the red line, at least until 2007, was leading in terms of return over all the other indices. And in particular, after the crisis, so after say about 2009, we see the light blue line, which is the Dow Jones Industrial Average, clearly getting out of the trough and having a fantastic increase afterwards, dominating all the other indices. The Nikkei 225, it's the purple line at the bottom, which seems to be very stable with not a lot of movement, not a lot of trend upwards. So let's calculate summary statistics for these monthly historical returns. So then what we see is that because now we look to monthly returns, the averages are a little bit more away from 0 if you, instead of in comparison with daily averages. So we see like 46 basis points for the Dow Jones Industrial, 23 basis points for the CAC 40. And then for the FTSE and the Nikkei, it's very small. We see also in this case that standard deviations are dominating the average return. So approximately 4% for the Dow Jones Industrial Average, 6% for the CAC 40, and then 4.7 and 5% for the other 2. What have been the worst 1-month returns? So minus 16% for the Dow Jones Industrial Average, minus 25% almost for the CAC 40, minus 21 for the FTSE 100, and minus almost 20% for the Nikkei 225. And then also somewhat upward potential there available. So it gives you quite already a good idea of how bad things could get if things go bad. Then, of course, because we are looking to a portfolio context, it's relevant also to include co-movements. In the bottom table, there are the correlations between the 4 indices. And what we see is that there is quite some positive correlations there. So that means that the global stock markets are related to each other. So the Nikkei is a little bit lower than the rest, but we see, for example, the FTSE 100 and the CAC 40 has a correlation of 87%, which is quite high. And also the Dow Jones Industrial Average with the CAC 40 and the FTSE 100 is as high as 75% or 79%. So that's high numbers. These are what we call unconditional means, unconditional standard deviations, and unconditional correlations, because what we simply did is we took the whole historical period and we used all the returns in this historical period to determine the mean, standard deviations, and correlations. So once I have all these individual elements, so once more, here you see how that portfolio of 1 million is divided over these four indices with the different weights, the means, and then also the covariances. A covariance element is determined by taking the correlation between 2 assets and multiply it with the standard deviation of the 2 assets, which provides then the covariance matrix on the right hand side for the individual returns. Then if I'm going to take the weighted average of all the means, with the weights 40, 20, 30 and 10%, that gives me a portfolio mean, which is equal to 25 basis points, 0.25%. And it gives me also, if I apply all the weights twice on the covariance elements, it gives me, and I then sum them up and I take the square root, it gives me a standard deviation for the portfolio return as well, which is 4.37%. So also in this case, we see on a portfolio return perspective, looking to monthly data, we see that the volatility of the portfolio return is clearly dominating the expected return. So you might almost say, well, let's simply ignore the mean return, but we leave it in just for completeness sake. So we have used this analytical approach to get to the distribution function of the portfolio return. As we saw earlier, then we have this multivariate environment with multiple assets which move and co-move in a particular way as represented by the means and the covariance matrix. And we can analytically derive the univariate distribution function for this portfolio return, and then afterwards, under the assumption that that's normally distributed, we can also very easily apply then the formulas for the value at risk and the expected shortfall to determine risk measures. So I've restated once more the formulas for the value at risk and the expected shortfall. The critical value at 1% for the standard normal distribution function, if you look that up in a table, it's minus 2.33. So that's the ZX. So if we fill in first the means and the standard deviation and the time horizon of 1 month in this case, and the critical value, then what it says is that the value at risk, so how much do you stand to lose, say, and you are 99% certain that this is the worst return that could happen, that's almost minus 10%, so minus 9.92%. So the second thing that we calculate as well, if things go bad and you are on the tail, so what's then the expected loss in the tail? That's the expected shortfall, which in this case, if you apply the formula, is minus 11.14. And these two risk numbers are important to us. And so what's nice is that this is all analytical, and it gives me a very neat and parsimonious way to determine the risk measures. And what I want to do next is I want to compare this case, so the minus 10% for the value at risk and the minus 11.4% for the expected shortfall. I want to compare them with different periods in the historical period to also reflect, say, what different regimes would do to the value at risk and the expected shortfall. So once more, these two risk measures, the minus 9.92% and the minus 11.4% for the value at risk and the expected shortfall on a 1-month basis, they are based on unconditional means, standard deviations and correlations. So it's the parameters that we put in for the market variables that also determine what kind of risk measures that we get out. And so what I want to do next is I want to start building different models for the standard deviations and for the correlations, so different ways to assess them, and then also use them as an input in the linear portfolio model to see what the effect is on the value at risk and the expected shortfall. So what we will do is we will use the expected weighted moving average, exponentially weighted moving average model. We use that both to update the variances of each asset in the portfolio and to update each covariance element in the portfolio of the assets in the portfolio. So let's look how this updating then looks for the standard deviation of asset J at time I. So I look to the standard deviation sigma of asset J at time I, sigma Ji, which is then the lambda times the variance of that asset in the previous period, plus 1 minus lambda times a shock that occurred in the previous period squared. So with u j I minus 1, I define the shock that occurred, so a deviation from the expected return, and I square that, and I give a weight of 1 minus lambda to that shock, and I give a weight of lambda to the previous variance. That gives me a new variance for time I, and then if I take the square root, it gives me the standard deviation. So I'm going to use this repeatedly for all the time points historically, and also for all the assets J in the portfolio. Same thing you could do for the covariance elements. So I'm looking at time I to the covariance between asset J and asset K, and that's really then defined as lambda times the covariance between these two assets J and K 1 month earlier, so at time I minus 1, plus 1 minus lambda times the shocks that occurred to both returns in the previous period. So again, these shocks are denoted with the U, so there's Uj for asset J at time I minus 1, there's Uk for asset K at time I minus 1, and these are deviations again from the expected return. I multiply these shocks with each other, and I give them a weight of 1 minus lambda. So that gives me an updating scheme also for the covariance elements, all the covariance elements in the covariance matrix. I use for all the updating schemes, both for the standard deviations of the assets and for the covariance elements, I use a lambda of 0.94. And I need to set starting values to begin with these recursive schemes, and the first standard deviations and the first variances and the first covariance elements that I set, they are set as the unconditional variances and covariances from all the historical observations. You could also set other values, could even set 0, and it means that the recursive scheme needs a couple of months to get updated before then the numbers become accurate. So very often we simply set the unconditional variances and covariance to at least start at a level where there is the average regime case. So here's a picture on the left-hand side of what this does to the volatilities of the 4 assets, and we see that the volatilities were high in the period between 1997 and then 2006, 2007. So when they went further and further down, they were at the lowest level. Then there was the crisis, so suddenly we see that the volatilities that they spike for all the indices, in particular for the CAC 40. And after the crisis, we see that, well, there is some time that the volatilities remain high, but after a while, say after 2012, we gradually see the volatilities go down to be back at the lowest level in the past 20 years again. So already here, in terms of uncertainty and in terms of risk assessment, it matters in what volatility regime that we are. Are we in an average volatility regime, in a high volatility regime, or in a low volatility regime? It matters for the risk calculations that we will do afterwards. So that's the left-hand side graph with the 4 volatility updates. On the right-hand side, there are the correlations between the 4 indices. And we see that some correlations always have been high, so around the 80 and 90s. And some of them were initially in the pre-crisis period, they were average, say around 40%. We see in the period of the crisis, so 2009, we see a spike of all the correlation lines going up as high as over 90%. And then afterwards we see some of them staying high and other ones gradually going down again. So also the co-movements, and so the extent in which the markets are integrated changes over time, and we see in the period where we could have, say, benefited most from diversifications, So from low correlations, we see that in fact that there the correlations tend to move up and get higher correlation levels. So now I'm going to redo the exercise that we did before. So we're going to use again the linear portfolio model on the 4 indices with the same investment as we had initially, same weights and then the same means. But now what I will do is, instead of using the unconditional volatilities and the unconditional correlations as we did in the first case, I'm going to look now to a particular day in history, which is March 2009, which was in the middle of the crisis. And that was in fact the moment where the volatilities and the correlations were the highest. So I've mentioned the numbers here. So 6.4% for the Dow Jones Industrial Average, 9% for the CAC 40, 7.2% for the FTSE 100, and 7.4% for the Nikkei 225. Also the correlations, you see very high numbers. So the lowest number is 0.82, but it's as high as 90%, 89%, and so on. So also strong co-movement, which then, if we use the volatilities and the correlations together, we can define the covariance elements, which are on the right-hand side. So this is the particular situation where you said, well, I have my portfolio, and I want to see what would happen if I'm not in a normal regime or in an average regime, but what if today actually we would be at the brink of a crisis? So tomorrow or next month, the crisis would appear. So what would then be my risk assessment? And that's why we use higher volatilities and higher correlations. So from the linear portfolio model, we know how to determine means and standard deviation for the portfolio return. So we take the weighted sum of the means, which is 25 basis points for the monthly expected return. And we take the weights times each covariance elements, so twice you do that, and then we add all these products, we add them up, and we take the square root, which gives us a volatility for the portfolio of 6.91%. Critical value for our value at risk assessments and for expected shortfall assessment is set to 1%, which means that there's only a 1% probability that things could go worse than the value at risk. I've restated the formulas for the value at risk and the expected shortfall. I look to a horizon of 1 month out of sample, and here we see that indeed both the value at risk and the expected shortfall move up considerably, as to almost minus 16%, minus 15.8% for the value at risk 1 month, and minus 18% for the expected shortfall. And then, of course, the third thing that we could do is we could look to a low volatility regime. So March 2019 actually is a low volatility regime. So I use from the exponentially weighted moving average, I use the volatilities and the covariances that apply there. So those are the inputs for my uncertainty in my market variables. I'm going to calculate the means and the standard deviation for the portfolio return from the means and the covariance elements of the individual assets in the portfolio at the 1% level. And here indeed I see that this is another conditional model, but now we are in the low regime, and here we see that the value at risk and the expected shortfall calculations give numbers as low as minus 7.8% and minus 9% for the expected shortfall. So it's nice about this linear portfolio model is that, that because we do not have to rely on simulation, it's very easy to plug in different assessments for the means and the standard deviations of the underlying assets to arrive at means and standard deviations of the portfolio return, and then to do all sorts of variants of risk assessments for this portfolio. Second topic for today is the handling of bond portfolios. We saw in earlier lectures that a bond has the bond price has a nonlinear relationship to the underlying yields and the underlying interest rates. So it's not easy to simply treat bonds as linear, because there's this nonlinear relationship with the yields, but also bonds have a finite maturity, so they will not simply have returns ad infinitum, but in the end there will be a pull to par, they will converge back to the principal value. So what we have seen is that there is a simplified approach where you could model the return on a bond portfolio, so dP over P, with a first order linear approximation where you take minus the duration of that bond portfolio times a change in the yield curve. So in this case we assume that there are no term structure effects, but that all yields with different times of maturity are identical to each other. But a little bit later what we will do is we will generalize this case to multiple points on the yield curve that could change with multiple risk factors, and then we use partial durations. So the principal component analysis is a very nice way to define in a model daily changes in the yield curve. So what it does is that it uses the historical variance covariance matrix of the daily changes in the yield curve, and this covariance matrix then is used to determine eigenvalues and eigenvectors. It's something that you not necessarily need to be able to do, so we will give you the numbers, but that at least then you could use those eigenvalues and eigenvectors to define a factor model as is stated over here. So what does the factor model say? It says, well, on the left hand side it says, well, how is the change in the 1 year yield, in the 2 year yield, and in the n year yield, so those are different points at the yield curve, how do they change on a daily basis? And what the model says is, well, you could very simply model that as a principal component matrix. That's the matrix with the elements PC11 until PCN1, PCN1 until PCNN, and you multiply them with very specific factors. So these factors are statistical artifacts, but as we will see later, we could also interpret them in a particular manner. So in this case, if we have n yields, then in principle the eigenvalue eigenvector decomposition of the historical covariance matrix allows you to determine also n factors. We will afterwards not use n factors, we will say, well, already a couple of them would suffice. The very nice thing about this principal component analysis is that these factors can be constructed in such a way that they have mean 0 and they are uncorrelated to each other. So then each effect is an effect that's not correlated with another effect. So that's reflected on the right hand side, where we say, well, these factors are normally distributed, that's the assumption, with mean 0 and with variance of sigma I square for factor I. So if I look to this matrix notation and I do the matrix multiplication to arrive at a formula for the change in yield I. So for example, that's the yield with the time to maturity of 1 year. And I want to understand how that 1 year yield would change according to this model. I simply multiply the factors times the row in the principal components matrix. So it says the change in yield I take the principal components in the ith line, in the ith row, and I multiply them with the factors. So I put an m here, so I take m factors, and the reason why I put m is because I allow the number of factors that I want to include, I allow that to be different from n. So suppose that I have 10 points at the yield curve, then it means that my principal component analysis gives me 10 potential factors with 10 standard deviations and also 10 by 10 principal component matrix. I could simply decide to use only 1, 2, or 3, or 4 factors. That means that instead of putting m equal to 10, I could put m simply equal to 1. If I put m equal to 1, then I say, well, I know that there is more factors to explain the change in the yield, but I only am interested in what the first factor does, so F1. So if I put m equal to 2, then I say, well, I'm only interested in what the first and the second factor does. And as we said earlier already, very often the first factor picks up most of the variation in the yield curve. But first and second factor is already enough, but 3 factors could be the maximum that you really need. So that's what you see at the middle of this slide. There you see the outcomes from the principal component analysis on this historical covariance matrix. And indeed, the first factor then has principal components where the first column has numbers which are not entirely, but which are very similar. So what we have said then is this is a factor, this applies to a factor that is in particularly concerned with parallel shifts in the yield curve. Most important of all the factors. The second factor has to do with is a slope factor, which has to do with rotation. So we see negative numbers with the low maturities, and then we see that moving up to high numbers with long maturities. So then an effect, say an impact of factor 2 would be that while the short part of the yield curve goes down, then the long part of the yield curve goes up. So that's a rotation. And the third factor has to do with the curvature change in the factor. But usually we say, well, certainly 2 factors would do most of the job. And then we see also the standard deviations of these factors also estimated. So what's important now is that we already had the linear relationship between a change in the return of a portfolio and the change in the yields that apply to that portfolio, because those were the partial durations that we will use. We now will go one step further, and we will try to write the relationship between the change in the portfolio value in terms of a change in the factors. So instead of looking to a change in the portfolio value and a change in the yields, we look to a change in the portfolio value and a change in the factors, and the factors build up to the yields. So what does that look like? We know from an earlier lecture that the change in the portfolio value is determined as minus the portfolio value times each partial duration for the different points at the yield curve times the change in the yield at that point in the yield curve. So what I will be doing now is I will be substituting this change in the yield curve, this delta yi, I will change it with the principal component model that is on top, and I put it already in a summation format at the right top. So if I substitute that then in this equation and I change the order of the summation, then I have the sum of j is 1 to m, and then the minus sign, which was before, the p-value, which was before, the portfolio value, partial duration, and the principal components that get in. And then between parentheses is something that I will calculate, and I will denote with delta j. You simply can do that. So what has happened now, I started on the left-hand side with a change in the portfolio value, which is then written as a combination of a partial duration times a change of the yield. And at the end, at the right-hand side, we see that we can rewrite it as the change in the portfolio value is a sensitivity for a factor, delta j, times the factor itself. So I've gone to another risk sensitivity and another risk driver. So the risk driver in the earlier case was the change in the yield, and the risk sensitivity was the partial duration. Now the risk sensitivity is what we will denote with this delta, which is a convolution of the partial duration and the principal component. And the risk factor are the factors from the principal component models. So the level, slope, and curvature factors, for example, if m would be 3. So I've stated it once more here what it looked like. So I'm back in my linear factor model. So where we earlier in this lecture we talked about the linear portfolio model, I've really rewritten the change in the portfolio model, but now for the bond portfolio in a similar manner. So there is a delta J times a factor. So the factor is kind of complicated to calculate, but it's simply a calculation. And the factors are the underlying risk drivers. I've denoted 3 of them here only because that's sufficient. Then, if I'm going to do the math to get to the distribution function for the change in the portfolio value, because the underlying factors are multivariate, normally distributed, and they have covariance elements of 0, it's rather simple to determine the return distributions of the change in the bond portfolio value. It's also normally distributed because all the means are 0 for the individual factors. The mean of the portfolio change is also going to be 0. And if I want to determine the variance for the change in the portfolio value, I need to take the squared value of the sensitivities times the variance of each factor individually and then add them up. And the reason for taking the squared of the deltas here is that if I take the variance of a constant a times a stochastic variable x, then what I do is, if I want to calculate that, then that's the same as a square times the variance of the stochastic x. So that's also what I do here. I take the variance of delta j times factor j, which is then delta j square times the variance of factor j, and the variance of factor j is then sigma j square. So if I have m factors, m could be 1, 2, 3 or more, then I simply add up these individual squared sensitivities times the variances to get to the variance of the portfolio. If I take the square root, then I have the portfolio volatility of portfolio standard deviation. And then I'm back in the very easy case of a univariate normally distributed random variable for the change in the portfolio value, and I can apply the traditional measures that we had before for the value at risk. So I've restated the formula here one more time. You take a critical value for the left tail of your distribution function, and you take a time horizon, which then in this case, because we do the calculations with daily data, is then also expressed in days. So capital T is expressed in days, and the Z is then again the critical value of the standard normal distributed distribution. So what we want to analyze now further as well, does it matter if I look to 1 risk factor, 2 risk factors or 3 risk factors? If I would include only 1 risk factor, then it would mean that I'm only interested in parallel yield curve shifts. If I include the first and the second factor, then I'm interested in potential parallel yield curve shifts and rotations of the yield curves. So that's the first 2 factors who account for that. And if I take into account 3 factors, so if I include 3 factors as risk factors, then it's the parallel rotations and curvature changes. And in doing this analysis, I really answer the question, well, how important is each type of yield curve risk? So I have my principal component model, and I have the daily, which is expressed in daily observation. So I also have the daily volatilities of the factors, which are expressed in basis points. So you should multiply them with 0.01%. And then I assume that I have a portfolio, and for this portfolio I've already determined, which consists of many bonds, and I've already determined what the sensitivity is for that portfolio if there is a 1 basis point change in the yield. So that's really the calculation that you do beforehand, where you determine the partial durations of all the bonds. You add them up, and then you multiply that with the portfolio value, and you put a minus sign. Then, since we only will be looking to 1, 2, or 3 factors, we only need 1, 2, or 3 principal components. So it's not all the principal components that are included. And what I need to do now is I need to rewrite the partial duration model where the yield is the underlying factor. I need to rewrite that in a model where the factors of the principal component models are the underlying risk drivers, and I need to define these alternative risk sensitivities, which we have denoted with the deltas. So I need to look to the relevant points at the yield curve, 1 year, 2 year, 3 year, 4 year, and 5 year rates, because that's where my portfolio is sensitive, which I see from the second table. So then I also take the principal components for the 1, 2, 3, 4, and 5 years. And I'm going to multiply these principal components with the price of the portfolio and the partial durations and the minus sign. So that's a multiplication of the second table as a row with the third columns, with the third table, and then columns wise. That gives me the deltas, which are then in the first line of the fourth table. It says portfolio sensitivity. And why does it say portfolio sensitivity? It is because these numbers that you see there, for example, the minus 0.08, says, well, how sensitive is my portfolio for a change in the first factor? So how sensitive is it for parallel yield curve change? And the second number, minus 4.4, now says as well, how sensitive is my portfolio for changes in the second factor? So how sensitive is my portfolio for rotations? And then the third factor says, well, how sensitive is my portfolio for curvature effects? So it's minus 2 in this case. So please note that this portfolio sensitivity for these factors is a combination of the partial durations and the principal components. So there is a combined effect there. And obviously what we see is that the portfolio is very sensitive for rotations, and it's not very sensitive for yield curve shifts, so for parallel shifts, because there's only minus 0.08. It's the combination of being sensitive for an effect and for the extent to which the effect could occur. And that's why we take the variances of the factors as a measure for, say, an extreme movement. We see that the variance for the first factor clearly is dominating. It's a factor that's much larger, so the variance is 306. Whereas for the second factor, for the rotation, the variance is only 37. For the third factor, it's 10. But it's then the combined effect of the square of the sensitivity of the portfolio times the variance, which does the job. And because the sensitivity for parallel shifts is almost 0, it's only minus 0.08. If I square that and I multiply that with 306, then the overall effect of that is only 2. Whereas if I look to the rotation factor, its sensitivity was much higher, minus 4.4. If I square that and I multiply that with the variance of the second factor, with the 37, then the effect is huge, 709. And then the third factor has a contribution of 41. So those elements provide me with a way to determine the standard deviation of my portfolio. If I would include only one factor, so only the first factor, then I'm only interested in, say, the number 2, which is then the total variance in that case. If I take the square root of 2, which is 1.4, that would give me then the daily volatility of the portfolio of 1.4. If I include the first and the second factor, then I need to add up the 2 and the 709, which is then 711. And then if I take the square root of those variances, so then I assume 2 factors are relevant as risk factors, then I have a daily standard deviation of 26.6. And if I also include the third factor, then I need to add up 2 plus 709 plus 41. If I take the square root of that, that gives me a daily volatility of 27.41. So clearly what this suggests is that if I would only include one factor, then the volatility would be quite low, whereas if I include the second factor, then the volatility moves up considerably to 26.6, and the third factor adds a little there. But it's apparently the second factor in this case, so that's where the portfolio finds its sensitivity. This portfolio is very sensitive to rotations. And that's then also reflected in the value at risk calculation. Suppose that we would have assumed that only parallel shifts would be relevant for this portfolio as a risk measure, then we would have determined the 1% critical value at risk using the 1.4 standard deviation for the portfolio, which would give me a value at risk of 3.26. If I would include the second factor as well, then of course the volatility is much larger, 26.6, and then applying the critical value at 1%, then suddenly I have a value at risk at 62.01, which is enormous. And adding the third factor means that that we will even get a higher number, but clearly the message here is that sometimes we think that we can rely on parallel shifts as being the dominating effect in our risk assessment for bond portfolios, but there may be portfolios, and this is a particular portfolio, where it's not so much the parallel shift that has an effect, but it's the rotation that has an effect. And it also then suggests, well, please make sure that you do not exclude the non-parallel shift effects that could have an impact on your portfolio. That's the message here. And that concludes this lecture. Thank you.